So this lesson's a follow-up to what we've been reviewing about the quadratic formula. So specifically, we're going to talk about how we know from the quadratic formula what types of solutions we have without actually using it all. So here's what we know already. So we already know that the quadratic formula is opposite of b plus or minus square root b squared minus 4ac all over 2a. We also know from previous lessons that when we're looking at a quadratic equation, it could have, when graphed, it has two x-intercepts, which means that it has two roots, because roots, remember, are the same as solutions. Or what could happen is it could have one x-intercept if the vertex is exactly on the x-axis, which means it has one real root. And the third case is that it never intersects the x-axis. In that case, we have no x-intercepts. But what it really means is we have two imaginary roots. So without graphing and without doing everything here in the quadratic formula, how can we actually figure out what type of roots we actually have? And that's where this thing called the discriminant comes in. Now, before we go on, just to let you know, do you remember this? Opposite of b over 2a? Where did we use that from? Well, remember we used that to find the x-coordinate of the vertex when it's in a quadratic equation is in standard form. And so there's a lot of hidden gems in the quadratic formula. And so that was just one of them. But this right here is what we're going to be focusing on right now. It's called the discriminant. Okay, so now let's go ahead and specifically look at how that discriminant works. So what happens is, in order to get an imaginary number, you have to be able to take the square root of a number that's negative. So this part right here is going to be what determines if our roots are imaginary or that we have no real solutions. We have, in fact, two imaginary solutions. So if that's going to tell us if our roots are imaginary, it also has to be able to tell us if we have two unique rational roots or if we have one repeated rational root, which counts for two, even though it's the same number twice. So let's look at why. So down here I have three quadratic equations. And so let's go ahead and we're going to talk about this one first. So let's see what happens. So if I go ahead and I've already plugged in my A, my B, and all you need to do is go ahead and do C. And if you notice, these three equations have the same A and the same B. It's just their C values that differ. So I'm going to go ahead and plug in my 1. And now I'm going to go ahead and evaluate the discriminant. So negative 2 squared would be 4. Negative 4 times 1 would be negative 4. So that gives me exactly 0. Well, what happens when you take the square root of 0 is you get 0, which means I'm going to end up with 2 plus or minus the square root of 0, which is 0, all divided by 2 times 1. And since adding and subtracting 0 doesn't change anything, I don't have to add or subtract something which differentiates my roots. I just end up with 2 over 2, which is 1. Well, that's exactly one solution. So this equation here has one solution. And what was the value of the discriminant? It was exactly 0. Okay, let's look at the second one here. So now value of C is 6. So I'm going to replace it there, and I'm going to evaluate. Negative 2 squared, remember I'm just going to do the discriminant, is 4. Minus 4 times 1 times 6, which is 24, gives me negative 20. Well, when I take the square root of a negative number, it's imaginary. So when I go ahead and simplify that square root of 20, I would get, or negative 20, excuse me, I would get 2i square root of 5 over 2 times 1, which is 2. Since all the 2's cancel, I get 2 divided by 2 is 1. 2i divided by 2 is just I, square root of 5. So I'm 1 plus I square root of 5, and 1 minus square root of 5 means I have 2 imaginary roots. And since I have 2 imaginary roots, what told me that I was going to be having those imaginary roots was that the fact that my discriminant is negative. Okay, and last but not least, let's look at this one. So my C value is negative 3. So if I go ahead and I evaluate my discriminant, I get 4. Negative 4 times 1 times negative 3 is 12, which gives me 16. And so I end up with the opposite of negative 2, which is 2, plus or minus the square root of 16, which is 4, all over 2. 2 plus 4 is 6. 6 divided by 2 is 3. 2 minus 4 is negative 2, and negative 2 divided by 2 is negative 1. So I end up with two non-repeated roots that are both real. And again, what was true about the discriminant, this time it was positive. So to summarize, okay, b squared minus 4ac is a part of the quadratic formula that we call the discriminant. The purpose of using the discriminant is to tell us what types of roots we have. And if we know what types of roots we have, we also know what the graph is going to look like as far as how it intersects the x-axis. So if b squared minus 4ac is greater than 0, in other words, a positive number, we have two real non-repeated roots. If it's exactly 0, we're going to have one real root, and that's because, just like this one up here, if I was to factor it, it would be x minus 1 times x minus 1, and both of those give me x equals 1 as a solution. It's a repeated root. Or, the last case, it could be less than 0 or negative, and in that case we get two imaginary roots. Here we are, and we're going to go ahead and talk about all the things we can tell just from the discriminant. So first, the discriminant, remember, is b squared minus 4ac. It's a subset of the quadratic formula. B is negative 2, A is 3, and C is positive 2. So I have negative 2 squared, which is 4. 4 times 3 is 12. 12 times 2 is 24. So if I do 4 take away 24, I get negative 20. So what does that tell me about my quadratic function? If I was to graph this, this is telling me it's less than 0. If the discriminant's less than 0, I have two imaginary roots, which means it's never going to cross the x-axis, which means my parabola has to be completely above the x-axis because A is positive. And we also know of other things. We know that it's going to be a little bit more narrow, and the vertex is going to be shifted a little bit left and right. But for right now, I know it's not going to intersect the x-axis, and because it's a happy parabola, well, I know that it's going to be completely above the x-axis. The other thing I know that is if I was trying to figure out what were the roots of this equation or the solutions to this equation by setting it equal to 0, I would have imaginary roots because of the discriminant. The rest of this lesson is optional, and it's going to talk about simplifying a square root. So if that's something that's challenging you, go ahead and watch the rest. If it's something you feel confident and you can do without error, you're done. Okay, so a little bit about simplifying square roots because it's a key skill that you need to make sure you understand how to do before you can work with quadratic equations, because a lot of times we end up having to do square roots. Okay, so if I was actually to multiply this out, I would have 2 times 2 times 2 times 2 times 2, which is 32. So this is equivalent to the square root of 32. So say I factor it. So I factored it and I got this, and I want to go ahead and simplify it. Well, every time I'm taking a square root of something, I want the square root to be something that's a repeated factor at exactly 2 times. So this pair of 2's comes out as 1, 2. This pair of 2's comes out as another 2. And this one has nothing to match it with, so it stays behind under the radical. What's 2 times 2? It's 4. And what I have left over under the radical, because I can't match it up with another matching factor, is 2. And that's because if I went ahead and I thought of it as the square root of 32, Well, the biggest perfect square that is a factor of 32 is 16, and the square root of 16 is 4. Now, sometimes the numbers are so big we can't really think of what the square roots are, so we have to resort to simplifying this way. So let's look at simplifying the square root of 20. So if I go ahead and I just go ahead and do 2 times 10, and 10 is 2 times 5, what this is saying is I have the square root of 2 times 2 times 5. So the square root of 2 times 2, it's a matched set exactly. I only went to them. So they go ahead and that pair becomes a single outside of the square root, which gives me 2 square root of 5. Square root of 54. Well, I know it's 2 times 27 because it's even. I know 27 is 3 times 9, and 9 is 3 times 3. So it's the square root of 2 times 3 times 3 times 3. So I know that with the 3's, if I have a pair, and I take the square root of that pair, it's the square root of 9, which is 3. What it leaves behind is the 2 times 3. So I have 3 square root of 6. Okay, square root of negative 45. Well, remember that this is negative 1 times 45. And 45 is 5 times 9. And 9 is 3 times 3. So what I have is the square root of negative 1 times 5 times 3 times 3. So what are things that are perfect squares? Well, 3's are a perfect square, so they come out as a 3. And negative 1, remember, is a perfect square. What's the square root of negative 1? It's I. So I have 3i square root of 5. Now, sometimes when we are solving quadratic equations, we end up having to do some division when we're using the square root method, but we still have to having to take the square root. So if you end up with a fraction and you're taking the square root, this is one of our properties of radicals, is that you can do it as the square root of the numerator over the square root of the denominator. So what's the square root of 16? 4. And what's the square root of 9? 3 4/3. Now the hardest type of radicals to simplify many times is these, where they have a fraction, but the denominator is not a perfect square, and it doesn't go in exactly into the numerator. So first thing you always want to do is check to see if there's any common factors in the numerator and denominator when it's a square root of a fraction. And in this case, 4 does go into 20 and 8. So I'm going to divide both of them by 4. 20 divided by 4 is 5, and 8 divided by 4 is 2. And that's about as far as I can go. If I do square root over square root, I still end up with the square root in the denominator. And this is one of those cases that, if you remember from geometry, you learned that you should not leave a square root in the denominator. You also learned this in Algebra 1, by the way. So we have to do something called rationalize the denominator. So remember, a rational number can't have a square root in it. It has to be something that we could write as a fraction specifically. So how do we go about doing that? So how we do that is we want to go ahead and remember a little trick. It says if I went ahead and I did square root of 2 times square root of 2, I would get the square root of 4, which is just 2. If I did the square root of 3 times the square root of 3, I would get the square root of 9, which is just 3. So the pattern is anytime I multiply a radical by itself, I end up with the number I'm taking the radical of, or the root of, by itself, square root specifically. So going back to our problem over here, we have the square root of 5 over the square root of 2. So the problem is right here in the denominator with the square root of 2. I can't have a square root in the denominator. It's like not starting a sentence with a capital letter. So I'm going to multiply it by the square root of 2 because square root of 2 times square root of 2 is 2. Problem almost solved. But with fractions, whenever you do the denominator, you also must do to the numerator. So I have to repeat that action up at the top. So when I do square root of 5 times square root of 2, I have the square root of 10. And this is actually the same value as this, but it's formatted correctly for mathematics. So that's called rationalizing the denominator. Okay, hope this all helped.